Welcome, everybody. Thank you for joining today's application webinar focused on random vibration testing. Before we get started, just a few housekeeping notes as always. A reminder that Lansmont is a member of the Physical Properties Testers Group, or PPT as you might know it, which is a collective of specialized brands in physical properties testing. PPT covers areas such as tensile and compressive strength, torque testing, textile analysis, and real-world dynamics like shock and vibration. Alongside Lansmont, our family of brands include McMesson, James Hill, and Alluris. To learn more about PPT or our individual brands, you can visit the PPT site. It's also got a section that deals just with our on-demand webinars from not just Lansmont, but from all the brands, and I will put a link in the chat box for your convenience. But as many of you already know, our host for today is Lansmont's VP of Technology, Eric Jonassen, and I'm Sharon Smorenberg, one of today's organizers. We are supported by a dedicated team across the United States, Europe, and Asia. But for today, we ask you to ask questions throughout the webinar. You can use the question box to submit any questions you have, and as always, we'll address them at the end of the session. The webinar again is being recorded, and you will receive a recording via the email address that you've registered with. And then, as always, feel free to share it with colleagues who couldn't attend, or just to keep it on file for you for your reference. We really appreciate that. And with that, I'll hand it over to Eric.
Thank you, Sharon. And hello, everyone. I'm going to turn my camera on real quick just to say hello before I get going. And it takes a second for it to come up, but there I am. Hi, hello, everyone. Yes, introduction once again before I start talking about today's topic, which is random vibration. Quite frankly, talking about random vibration, just even commenting to Sharon earlier, is a topic that likely could easily use a day, a week, or a month to discuss in some cases, even if you're doing studying that type of content in mechanical engineering. So a bit challenging to try to figure out how to cover it in half hour, 45-minute, or even an hour session. So I'm going to do what I can with the focus on trying to keep it as simple as possible in thinking in terms of who Lansmont's key user audience is, as far as our technologies, our instruments, and our vibration testing systems. So I'm going to turn my camera off, get into my content, and I'll be back at the end of it. I'll turn my camera on, happy to answer any questions. Let me go ahead and turn that off and move forward here with my slides. Hopefully they're playing. Showing some exciting vibration signals on the screen right now. And again, what we're really focused on here is random vibration. How to make sense of those signals in the real world and translate that into something you can use in the laboratory on a vibration test system, which again, probably many of you who are attending are familiar with both sides of that, but might not understand the process of how that goes. Really, it's not trying to really be promoting the field to lab idea here so much myself, but that's the process. How do you take that data from the field and convert that into something that looks like this? How do I make sense of that? And so just to revisit a little bit on the last webinars that we delivered, which were really focused on sine vibration, it's in simple terms, it's good to revisit that as we move forward with random. So when we talk about sine vibration, we describe that in terms of a sinusoidal waveform in terms of its amplitude and its frequency. So if I plot a sine waveform, there it is. It's pretty, it's simple, it's clean, it's easy to understand that we have an amplitude associated with that signal. That is basically, 0 to peak, which is in this case a 1G amplitude in terms of the intensity or the amplitude of that signal, and we can describe that in terms of its frequency. So the frequency of a sine wave means, basically the time to complete one complete cycle of that sine wave. And if we know the time that it took, we can calculate the frequency of that sine wave. So in this example, that sine wave required 1 second, to complete its full cycle. So in calculating frequency, it's basically the inverse of that time, 1 divided by that time. So in this case, if it took 1 second and we have 1 cycle, that means that waveform has a frequency of 1 hertz. Pretty simple stuff, right? It's pretty simple and pretty clear as we look at that clean sinusoidal waveform. However, switching gears and saying, well, what about this? What about this signal? What about the amplitude? How would we describe the amplitude of that real vibration measurement that was made from out in the supply chain? How do we describe the amplitude of that? Is it just kind of where the peaks are, the absolute peaks of those signals on the plus or minus side of that? It's not. And then, how would we describe the frequency content of that? It's not a clean sine wave, right? There's a whole bunch of stuff going on there. It basically looks noisy because there's a lot of different content associated with that signal. So it's not so easy, it's not as easy as looking at a sine wave to describe what the amplitude is and what the frequency is, or the frequency content of that waveform. So that signal is the perfect kind of example of what we call random vibration. That's where we go from sinusoidal to random vibration. And how do you define random vibration? There's a number of maybe different ways, but a definition is motion which is non-deterministic or non-periodic, meaning that the future behavior cannot be precisely predicted. It's random. We don't know what's coming next. We don't know what it's going to look like. We can't predict what it's going to look like in the time domain because it is random. So it's challenging compared to sine. And if it's difficult or challenging to describe that type of motion and understand that, why do we even bother with it? Because that's exactly the type of motion that occurs in real world transport environments, whether, it doesn't matter what mode of transport you're using, air, rail, intermodal, over the road. Anytime you're moving, you're experiencing vibration input, oscillations, and it's very hard to predict those motions in terms of their amplitude and frequency. So when we talk about random vibration, we can describe random vibration in terms of time average intensities, and I'll explain that here moving forward. In terms of time average intensities, we can describe random vibration in what we call the frequency domain. I'm going to show you that as well. And we do that in the frequency domain by using what we call power spectral density plots, PSDs. You hear PSD referred to quite often in our world, either on the measurement side or on the testing side. Another way of describing this is depending on where you are in the globe, is acceleration spectral density plots, ASDs. But in our world, in our history, in the standards associations that we work with, most of the people probably even attending this event, be it ASTM, ISTA, ISO, MIL standard, for the most part, these are the random vibration is described in terms of power spectral density plots. So that same time domain signal, so that's time domain. You see I highlighted with a couple rectangles. This is acceleration on the amplitude side and the y-axis versus time. It's a time domain signal. And let's say this, in this case, this is about 2 seconds of vibration energy in the time domain. But we can convert that or transform that signal into the frequency domain. And so now you see, if I highlight the axes here, we have something called PSD, which the units are G squared per hertz, which can start getting into, that you can have a whole discussion on understanding what that term means. But in the simplest of terms, it means intensity, right? It's amplitude. So it's not acceleration, but it's a form of power or acceleration on the y-axis. But now we're describing it in terms of frequency versus over here where we're looking at it in the time domain. So that 1-2 second segment of vibration analysis can be described by its own individual PSD plot. And so we can say PSD plots describe the spectral content, meaning the frequency content, of a time domain signal or time domain signals and their associated intensity. What does that mean? You know, I always jump back to thinking of vibration in terms of sound, because sound is vibration, just different frequency range. But when we look at a PSD with frequency, you know, low frequency on the left-hand side of this plot here, high frequency in the transport environment, high frequency on the right-hand side of this plot. Well, if I think of it in terms of music, low frequency means bass. High frequency means, I'd say, I guess, more treble or tingy or ringy types of sounds. That's what we're really doing. You know, this is a standalone image of a sound or signal analyzer that would be used to characterize sound or things like music. So if I play that or animate that, you can see it's jumping all over the place at the different frequencies based upon the variety or variability in music. The reality is in transport, you don't get that extreme of variability across the spectral shape. So, you know, what that video little animation ended there with was just showing that. I'll play it one more time. Think of this more evident of what music that changes, singing instruments, so on and so forth. But transport right there, that the shape really remains kind of constant. Yeah, the amplitudes go up and down, bounce up and down, but the shape doesn't change so much of the frequency domain profiles. And why is that? Well, this is another video that I'm going to share here, and it's got sound, so I'll stop talking. But this is a camera that was inside an intermodal container with loads, you know, so it's cameras on the ceiling here of an intermodal container looking across that intermodal container at unit loads. And you'll obviously be able to see motion when I play this, but what you also do is you hear it, right? You hear it. And when you listen to the vibration, when things are rolling down the road, you can almost think of it as what it sounds like when you're flying. If you all have, you know, experienced flight and the sounds, which is kind of that, you know, monotone drone of actually a relaxing sound. And it's similar even going down the road in a car, you know, and but it's the same in the back of a container. It might be a little bit noisier, but it's kind of, the sound doesn't really change. So listen. Not crazy exciting to look at, not crazy exciting to hear, but there are some subtle changes in there. But for the most part, the sound is similar. You know, the volume might, you know, go up or it might go down somewhat, and you might hear some rattling of different things and rumbling, but that's the signature of that. Let's say the spectral shape of that doesn't really change. It just goes up and down while the container is traveling either down the rails or down the road. So what I like to say is PSD plots are the signatures or the fingerprints of various transport modes. And so what does that mean? Well, in truck, parcel shipments, rail shipments, jet, aircraft, turboprop, even sea vessels, each of those modes likely has a PSD plot that people in the testing community use to simulate that type of energy. In this case, on the one on the left is a truck, a steel spring truck, a truck trailer with a steel spring suspension system. That's a very common profile that's used. For instance, this is out of an ISTA test profile or test procedure. And that's common. That's a fingerprint, you know, I'd say again, or a signature of a leaf spring truck trailer. And even though this is an industry standard profile that's being shown on the left, if I go out and measure this myself tomorrow, or the next week, and I'm measuring a steel spring truck trailer, it's going to look like that. It's going to have that signature. Whereas like an air ride trailer would have a different one. It would look different. It would be subtle, but it's different to the point where if I see that type of data from measurements, even if I wasn't involved in measuring them, I can likely predict that says, oh, you ship that on an intermodal container. Oh, you ship that on a rail car. Oh, you ship that on an air ride trailer, because they do have these signatures associated with them. When we talk about the intensity of a PSD plot, that intensity is calculated or equal to the area underneath the PSD plot itself, the curve of the plot itself. So same thing, this is the leaf spring truck profile. If we look at that profile, that's included or referred to in ISTA 3B, 3E, 3F, that profile, PSD profile, has an intensity that's described in terms of its GRMS. And that basically means, yeah, the intensity of the profile, how severe is the profile. And so that profile right there, and if you were to run that on a machine in your laboratory, likely would have you would have a GRMS associated with it of 0.54. Well, where does that number come from? It's equal to the area underneath that curve, the complete area. It's just only, obviously in the Y scale, it doesn't go to absolute zero, but think of it as the area underneath that curve. So the higher those peaks are across that same frequency, if I have a profile with higher peaks or more area, it's going to have greater GRMS associated with it. If there's less area, it's going to have lower GRMS associated with it. And you can think of GRMS once again as being intensity or energy. So higher GRMS, higher energy, lower GRMS, lower energy. Another thing to point out, this is a plot with really two different PSDs overlaid on top of one another. And these are basically that same leaf spring truck profile in the green versus the old ASTM, what I'll say is the old, is the original ASTM truck profile that was probably developed in around 1980 and was updated in the 2016 timeframe. And both of those, the point here is that both of those profiles have basically the same GRMS value associated with them, the same calculated intensity, let's say 0.5 GRMS, one's 0.54, one's 0.52, but I'd call that basically equivalent. But the reality is they're not equivalent. So even though the GRMS values are similar, there's differences. And remember, if you think of the areas underneath those curves as being equal to the energy, you can see where there's differences, right? So in the green one has more energy in the low frequencies from, let's say, 1 to 4 hertz. It's got more energy, meaning more intensity or displacement occurring in that frequency range as compared to the old original ASTM truck profile. And then from 4 hertz out to about 30 hertz, there's quite a bit more energy included in the old ASTM profile. In fact, let's say at 10 hertz, you've got about 20 times the amount of energy being input, because again, these are log scales. So if I look at the Y-axis here, any change or any one of these divisions is really, you can think of as a 10 times change in amplitude, either greater amplitude from here to here or 10 times less from here to here. So in this example, this older profile would have about 20 times the overall testing intensity at 10 hertz. And, even here, from here to here, it's about 20 times more intense than the current profile. So yes, the overall GRMS of those profiles is similar, but you really need to think of these tests in terms of where across that frequency domain, where is the energy being input to the table, the vibration test table, and then eventually into your test products. Because these are not equivalent. And one could cause you a lot more problems than the other, depending on whether your products or unit loads have sensitivity or resonances or respond at those frequencies. For instance, a unit load might start to jump and bounce in the back of a trailer or an intermodal container at around 10 hertz, because that's where its natural frequency is. And if that was the case, and you're running that old ASTM test profile, you're going to be shaking it, or it's going to be, you're going to really be driving the heck out of it with that test profile. And very likely, I would say, from my experience, inappropriately, because it's going to be inputting energy at a frequency and amplitude that doesn't occur in a real world on the back of a truck or in the back of a trailer. So just wanted to show that comparison. So if random vibration occurs in the time domain, meaning, again, y-axis amplitude, but x-axis time, how do we get it into the frequency domain? How do we make that transformation from time domain on the left to frequency domain on the right? Simple terms, we use what's basically the Fourier theory, which basically says any time domain waveform can be analyzed as a combination of single frequency sine waves. And I'll show you what that looks like. And quite frankly, when you're measuring things and doing testing, all of this stuff is calculated for you. So the idea here is just to show you basically there's a method to the madness, and it's based on the Fourier theory. So if I look at this real world time domain signal that was captured from the back of a truck, there's three different colors shown here, which refer to the three channels, X, Y, and Z, or vertical, lateral, and longitudinal measurements made from the back of a truck using a data recorder. So there's a lot going on there, but if I focus right on just on the vertical vibration, which in this case is the most intense vibration that you experience on the back of a truck, and which is what is performed, for the majority of testing that's performed in a laboratory, it's vertical vibration testing. So I'm going to focus just on this vertical signal. It's the same signal I showed in the previous ones in the red, but now it's yellow. And this is about 2 seconds worth of data, right? So this says from left to right, this says time 0. Out here it says 2.048, but basically think of that as 2 seconds worth of data, and the y-axis being amplitude. Well, I can apply things to this, like bandpass filtering, okay? Bandpass filtering means I'm going to focus on certain frequency bands to see what's basically hidden, I don't want to say hidden, but buried within that overall noisy looking signature. So for that yellow signature in the background, if I bandpass filter and say, I only want to look at the one hertz or less content in that signal, and if I apply that filter with software, that is what the result is. So that is that nice looking, smooth, wavy looking trace on the screen. That is the less than, basically 1 hertz signal or content within that noisy yellow signal, real world signal behind it. And that's the 1 hertz or less than 1 hertz. And then if I change my bandpass, I say, well, what about the 1 to 2 hertz content? Well, it changed. So this is the less than 1 hertz. This is the 1 to 2 hertz. That's the low frequency content from 1 to 2 hertz. What about 2 to 3? 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and 10 to 11. You see all of those, as I apply that filtering and focus in those areas of a frequency range, bands, very tight bands, that's the signal or the contribution, in this example here, 10 to 11 hertz, that, believe it or not, is in here. It's in this noisy signal in the background. And we can dissect that. And that's what the Fourier transform basically does, is goes through and looks at, and I only showed, basically 1 to 11 hertz, but it does that across the whole frequency range that we're interested in when we do these types of measurements, okay? So if I export all those signals, which I can do, if I export those same signals, the less than 1 hertz, there is the 1 to 2 hertz band, the 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, so on and so forth, all the way out to 11. It looks very noisy, right? I basically overlaid everything I just showed you. I dissected, pulled them out, I export them, and I overlay them in Excel, and it looks like a mess. And it is. But all that content was in that signal. Well, if I add them together, or I sum them, literally, and I do that in Excel. If I sum those waveforms together, this is the result. That green trace is the summation of all that energy content. Obviously, I stopped because I didn't want to, do it all the way out to, let's say, 200 hertz. Too much work for me. But just in this one example, if I sum those together, that's what it looks like, calculated or generated in Excel. Well, if I now pull up that same field data as captured by one of our data recorders, and I apply a bandpass filtering to that noisy signal, and I say, okay, instead of just looking at 1 hertz or 1 to 2, 2 to 3, 3 to 4, all those different things, if I say, you know what, show me everything in this example, if I just filter everything from 1 to 11 hertz, this is what was generated in the filtered signal in our Saber Xware software. Well, look at, here's what I actually did in Excel. They did these completely opposite. I exported all those signals, I added them together, got this green trace, and if you look here, it's exactly the same. It's exactly the same trace. So the point there is a method to the madness of where or how the waveforms can basically be dissected to understand more about very specific frequency content. Okay, so now if I go back to that 1 2-second event, the real world event where it's really noisy, the way I then create a PSD, this is the PSD for that event. So if I'm going to back up, and you see at the top of the screen here, it says event viewer signal 499. This is a 2-second signal that was captured during the measurement, and this is the time domain acceleration that was captured. This is the event PSD for that same signal, okay, where it was transformed into the frequency domain. So how is this plot created? Well, there's that less than 1 hertz frequency content that, through filtering or through the Fourier transform, we can say, okay, show me the content of, basically 1.5 hertz. And once we generate that and we do some averaging, the average intensity of the signal across this time domain window, we plot it. We say, okay, I'll pull that out, I'll dissect and find out what kind of 1.5 hertz energy is there, come up with an average intensity, just which computers do for you, and then I plot it on the PSD. And then I say, okay, what does it look like at 5 hertz? I can pull that out. I can do some averaging on that overall amplitude across that window, and I plot that. And then what does the 10 hertz look like? And I do the same thing, do some averaging, plot that. And of course, that's done, not just, those are 3 little examples, but imagine across this whole curve, this PSD curve, there's, potentially hundreds of those analyses that are taking place. Everywhere you see a peak on one of these PSDs from the field, so basically means there is math being done at that point. So there's no doubt 1 here, there's 1 being done here, 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 here. So it's hundreds of different points where you have the ability to dissect the time domain signal, create basically average time history or time intensities, and plotting those on your PSD plot. And this is one PSD that was created from 2 seconds of real world data. And that's all it is. It's I can create a PSD on that, just 2 seconds. But the reality is, when we do transport measurement, we're recording things like, probably hundreds, if not thousands, if not maybe even tens of thousands of 2-second events, or 1-second events, or 4-second events. So we record hundreds to thousands of those PSDs, and then we average them together. We somehow statistically combine those. So you see here all the individual PSDs that were recorded, and this is a summation of those that's being calculated as we average those together. And that's just the simplest way of looking at this data when we do transport measurement, is instead of just creating a PSD for one event, we typically gather thousands of events from transport and average across them, or do math across those. And so this next example is from our software, our SaverXware software. Back to how these come to life, or where these PSDs are generated from, is if we do a measurement, and just instead focusing up here at this red information at the top of the screen, this is the start of a measurement. This just says September 2nd, 2021, and this is September 3rd, 2021. If in each of these red bars was, and there's thousands of them, but they're those 2-second events. They represent the amplitude, the Y amplitude. The height of the bars represents the amplitude of the PSDs that were captured, and there's thousands of them. So what we do is we average across all of that data. So there's thousands of PSDs, and this is going to play a video. If I average across those, you get a summary PSD. And when I generate that summary PSD, I'm able to export that summary PSD from the software. I export that, and then I go to my vibration controller, and I'm able to import that data, that very same data that I just exported. I pick the appropriate channel that represents the vertical vibration, and I create a test PSD. It's simple as that. It's kind of like for us, the poster child of our little field to lab process, but it works, right? It works. I'm able to generate those summations from field data, create PSDs, and then I'm able to import those. And this is not something that's exclusive to Landsmont or any company. Any vibration controller can import. You can either create your own PSDs, or you can import data like this. It's a very simple data, basically Excel or ASCII files, to create these. And what this shows, basically this is that 2 different softwares being shown here. This is the summary PSD that comes out of our field data summation, SaverXware. This is what it looks like. I exported it and I imported it here, and and it's the green channel. Why is it the green channel? There's 3 channels going on down here, but the green is the highest intensity, and that's because it's representative in this example of the vertical vibration that was measured during that journey. Well, I export that, I can import it into my controller and be off and running, simulating the energy on average that occurred during that 1 day of measurement. Okay, so where do we use random vibration PSDs? Well, most people are familiar with them. That in the Landsmont, I'm going to say my world, or our kind of customer or testing community, we use them they're referred to in ASTM D4169. They're used in the ISTA test series, 2 series, 3 series, 4 series, even 5 series. But there's random vibration referenced in all those. There's random vibration referenced in ISO 13355, MIL standard 810, just as examples. There's more, but these are probably some that a lot of people have familiarity with. And we describe those, especially within ISTA, we describe those PSD profiles as general simulation profiles. They're generalized vibration profiles that simulate the energy content that you would experience if you ship using different modes. And there are different profiles. So I'm just showing a broad kind of cross section, ISTA 3A, ISTA 3H, ASTM 4169, the ISO 13355. And within these, you see there's different traces and shapes. Over the road, pickup and delivery, low pressure test, meaning more like an air test, leaf spring profile, air ride profile, rail car profile. So they're these generalized PSD profiles that, once again, simulate the energy content that you could expect to experience if you ship using those different modes of transport. So we call those generalized simulations or general simulations. You also can do customized test plans using PSDs, which is kind of what I just showed. Really the ability to capture field data from various transport modes or various transport lanes and summarize that data and use that to drive customized test plans. If some of the general ones don't work for you or don't work well enough for you, you do always have the ability to go out and kind of create your own. And there's kind of methodologies for how you go about doing that. And what's important to also understand is that even all these profiles, standard profiles that are shown here in the background, ASTM, ISTA, ISO, those profiles, came from somewhere, right? They didn't just pop up. Someone didn't just, pull them out of thin air and say, let's just use these shapes and call that a truck profile. Once upon a time, through the standardization efforts, test development, test standard developments, some type of effort was made to go out and characterize these environments and measure them and define these profiles even from the standards perspective. So they are based somewhere in their history. Some go back quite a ways, some are more current, but they are based on measurement or observation that took place in supply chain once upon a time. And they continue. We all continue in the standardization world, standards organizations, to look at different modes of transport at different geographic areas, maybe meaning around the globe. Is it different depending on the type of equipment you might transport? For instance, if you're shipping things in the cold chain versus general transport simulation, is there any reason why a test profile might look different? So there are reasons, that people continue to dig into, I'd say, the customized test plans or updating of standards plans. But we use these PSDs and all, these are probably the most common industry standard organizations and test references where we use PSDs. And so when we look at running a vibration test in the laboratory, and which is I'm going to focus on in the next webinar, and we'll actually go do random vibration testing, and I'll try to eventually point out some of the differences associated with how you program one of these PSDs, the shape and the amplitude of the frequency content. But when we play one of these on a vibration system, which I'm going to animate this, what you see on the screen is basically right here. This is what you see on your vibration system. There's actually not a lot going on, right? It's a frequency domain view of the test. But reality is there's not a lot of change that you see. It's not really very exciting to look at because there's not really much occurring there. But what's really happening behind the scenes is, if you click on that window right there, that's the time domain signal. Now it's not frequency, that's the time domain signal that has all that frequency content that is encased or bounded by that green line that you see at the top of the PSD chart. That speaks to the frequency content that's in that time domain signal. So what a vibration controller does is it says, okay, when I do this testing, let's just pick this point. This is 1 hertz, 2 hertz, 3 hertz. It says I'm continuously, when I'm running a test, going to send out a signal over to the vibration machine that has 3 hertz content to it. And on average, its amplitude of that 3 hertz content is going to be this. In the y-axis, let's just say it's 0.02 G squared per hertz. It's going to have that average intensity, and it's doing the same thing for 4 hertz, for 5 hertz, 6, 7. It's sending out a time domain, a random time domain signal that on average has content at each of these frequencies across this whole spectrum with average intensity that is bounded or directed by the PSD profile, the green line. So the white line that you see, jaggedy white line, that changes. I'll run this one more time from the beginning. That updates every about second and a half. And what that's showing when it comes back up, there you see the update rate, right? It's like one, just, and I've sped this up to play it, but the updates are like 1.5 seconds or so, and it's showing on average that it's what the reality is of those measurements at those different frequencies. And we're asking it to do that green line. So you expect the white line at any given time to basically be on top of or very close to the green line. But the reality is when you watch this signal here, and if I just drag it across, it's changing, right? It is changing. It's going up and down. It's changing. Sometimes it's got more amplitude or less amplitude, even at, let's say, at 3 hertz. At any given time, the amplitude might, at any given time of 3 hertz, could be high and it could be low. And there are, kind of rules for random vibration control that says how much higher or lower can it go than this point. But on average, also at any given time, that calculation is made on average, in this case, like 1.5 seconds, that average better be here. So we allow it to move in reality through, again, standard random vibration control. We allow it to move around that average, plus or minus, but at any given time, the average intensity better line up on the boundary that we set with our PSD profile, drive profile, okay? So a little bit about enhanced simulation. Remember that the PSDs for the profiles are general. They're general, for a truck trailer or for a rail car, box car, intermodal car, or even an aircraft. They're general, and they're based on some type of averaging that takes place. But if I recall this same data set that I showed earlier, so September, this one was a day's worth of vibration measurement that took place, remembering that each one of these red bars represents, let's say, a 2-second segment of acceleration time history, vibration time history that was measured. And so what's important to realize is that if I do that summation average across all that data, which could be thousands of events, the average GRMS, because that's the Y scale here, is GRMS, 0 to 1 GRMS, the average intensity that we would get in this case is about 157 GRMS, which is where I drew the dotted line across the data there. So that's fine, that's what that means. And so if I exported that, I could run a test that had an average GRMS of 0.157, and you might say that simulates the ride. And what I would say to that is that, well, it might, but the reality is, this is the average. So some of the vibration that was experienced was less than the average, and some of it was greater than the average. I don't really care so much about if it was less than that, but I am, as a shipper of products, concerned with the big stuff. So if I run a test at this intensity, well, what about these big things? What about that big thing, this big thing, this big thing? All these other things that occurred at a higher intensity. If I'm only testing at this intensity, am I at some risk that these types of inputs that happen in the real world could contribute to damage in my product? And just talking about vibration testing in general, there are 2 things that we is generally accepted that cause have the potential to cause damage. One is the time exposed to vibration, how long something is exposed to vibration, and the amplitude. So how severe is the amplitude? So it's time and intensity. Both of those things contribute to damage. So if you artificially, in my opinion, discount or whatever, underappreciate some of the big intensities that occur in the real world, you might be leaving yourself susceptible. So we have a way of looking at data with an advanced, what I call advanced statistical analysis and summation, which can potentially be used for more accurate simulation of an environment. So what I'm showing on the right-hand side are PSD plots. Looks a little different than what you've seen up until now, but that is in the green area here. These are PSD plots. There's green, there is yellow, and there is orange. Think of it as like a weather radar, kind of a radar plot, where there you see orange. That means there are higher concentrations of data that occurred at those levels. And so if you think of this as PSD data, instead of generating one average summary PSD from transport data, in this case, I can say, well, I want to have a little bit more clarity or resolution as to that data. So if I record, let's say close to even 100,000 or 90,000 events in a data set, how do I look at that and say, you know what, in addition to the average, show me what the 70th percentile of all that data looks like. What about the 80th percentile? What about the 90th, the 95th, and the 99th percentile? And as you see, as I scroll through that, up at the top, it's kind of summarizing what the GRMS intensity is at that level and how much of the transport in terms of events over here occurred at that level. And if you think in our examples, it depends on what your event, the time of your events are, but if they're 2-second events, I can quickly do math on this, right? And say, how much of the journey occurred at that level, how much of the journey occurred at that level, and what it shows is a trend. Yes, some really big stuff, comparatively big stuff, intense vibration occurred, but for a short period of time, right? So I can tell you exactly. I can't right here, but 2 seconds per event, do the math. You can say how many minutes occurred at that intensity. I can also say of that total journey, how many minutes occurred at this intensity, so on and so forth. And so that becomes powerful, in my opinion, because you can use that to, for instance, build a test queue, a random vibration test queue in your vibration controller. This is, again, not exclusive to a Landsmont thing. Anybody could do this. You basically build a queue that says, you know what, I'm going to run, let's say, along maybe 80% of my test or 50% of my test at the average intensity. I'll run 20% at the 80th percentile. I'll run 10% of the test duration at the 90th, and 5% of the duration at the 95th percentile, and maybe 1% of the test duration at the 99th percentile. And I run it at those levels because that's how it really, for the appropriate time, because that's how it really occurred or occurs in the real world. So it allows you to really kind of fine tune if you're interested in finding that line of not over testing and not under testing. There is time compression that occurs typically in the standards community, and it works. It has worked for many, many years, but sometimes it can run a risk of, again, either over or under testing if it's done arbitrarily. So this almost addresses the idea of time compression, but it's not really, because the time that you're using, if you follow this approach, follows the time that it actually occurs at these levels in the real world. So this is kind of a nice way of approaching, I would say, more enhanced simulation testing. Okay, so the last thing I want to close on here is this. I want to highlight this paper. So there's a paper that that we put together called Random Vibration Primer, and it was put together by our chief engineer, Kevin Gilman, who is kind of a brilliant person, is a brilliant person, was a brilliant person that was with Landsmont for his entire career, 45 years or so, where it explains a random vibration in much greater detail than I did in this presentation. So not going to go through this, but I'm just letting everyone know that this paper will be made available to everyone that attended the webinar, because it goes into detail describing what is PSD, what is power spectral density, what is G squared per hertz, which refers to the intensity of a PSD breakpoint. What is it? How is it calculated? How is the GRMS calculated? So this gets into a little bit more of the detail for those of us nerds, people that are interested in digging in deeper. It's too much for me to cover again in one of these sessions, but we'll make this available. I wanted to let you know that as well, because I find it to be actually very informative. And then last but not least, random vibration. This was kind of to talk about the idea of what is it, where does it come from, in the real world, how does it transform into something that can be used in a laboratory environment or that stands behind the industry standards. And the next one we're going to do will be another live webinar where I'll go up into the lab in my examples or my location. I go up to Michigan State University, where we'll do some random vibration testing and kind of touch on some of the differences associated with different profiles, and to be able to visualize, like you're seeing on the screen right now, what the contribution is in the frequency content when we put in one of these profiles. If you look where the breakpoints are, where you have a lot of low frequency energy versus a little low frequency energy, what are the implications from a testing perspective? What does that look like? So 2 weeks, we will go into the lab and do some playing around with the equipment itself, and can even show you that the whole idea of the field to lab process. I'll probably do something like record my drive up to the lab and show you how I can play my car ride on the machine when I do that. And with that, I am going to stop, ask Sharon to come back in, and try to answer questions. I realize again, I go long. It seems like I do that, but I'm actually happy I was able to make it through it in less than an hour, because it's heavy, can be heavy subject matter. So happy to entertain any questions. Obviously, long-term, happy to answer any questions either by email, call, so on and so forth. So Sharon, if you're back, I will ask you.
Thanks, Eric.
Yeah.
Thank you very much for that. And obviously it was an interesting topic. There's a lot of questions already. So I would say, let's see how many we can get through. We can always distribute answers via the on-demand as well, but it would be nice to get through a few of them.
Sure.
And obviously for those people who haven't put their questions yet, now would be the time for you to do so. So the first question is there a standard amount of time domain data that is used for looking at frequency domain?
Well, in the real world, let's say if we're going to record it in the real world, and in my examples I referenced 2 seconds worth of data per event, and there is a reason for that. And again, that's addressed. Even, let's say ISTA's got data collection guidelines, so it's addressed even in there, and we have written papers on this ourselves. So there's reasons why you set the recording window to be a certain amount per event, like 2 seconds. And there are reasons why you would set a data recorder to sample at or collect the data at a certain sampling rate, frequency. So in short, let's say the recording window. So if I want to see 1 hertz content in a data signal of acceleration versus time data signal. Remember, 1 hertz has a cycle. You need 1 second, at least 1 second of data to be able to see 1 hertz of content. Why? Because 1 hertz signal requires a time period of 1 second to be able to see a full cycle. So I need to record at least for 1 second. If I record for a time segment of 2 seconds, that means I would be able to resolve down to a half a hertz on the low end of a PSD frequency summary. So, the longer the window, the lower the low end of a PSD that you'll be able to resolve in the frequency domain. What about the high end of a PSD? So that's based on the sampling rate of the data recorder, data acquisition system. So if I want to resolve, let's say up to 500 hertz on the high end, so there's the low end, which might be a half a hertz, might be 1 hertz. I want, what do I want to see? Transport, like the PSD profiles that you see in industry standards for our world, typically in the 1 to 200 hertz range, I would say, generally speaking, 1 to 200 hertz. But if I wanted to record or see up to 500 hertz, then I would need to record using a sampling rate of twice that frequency, at least twice that frequency. So I want to record, see up to 500 hertz, I'd want to sample the environment at 1,000 samples per second. If I wanted to record only up to 200 hertz, then I would, or see data up to 200 hertz, then I'd want to sample my data at least at 400 hertz. For us, typically that means 500 hertz sampling rate to be able to resolve half of that, which would be 250 hertz. So I don't know if that makes sense or not, but that's kind of the method to the madness. You need to record long enough windows to that the time of the window allows you to set your low end frequency band on your PSD, and then the sampling rate, how fast you're capturing data, allows you to resolve the high end of your frequency PSD.
Thank you. Next question. How are these real-world profiles captured? Also, are there profiles capturing EV transit models yet? Any notable differences?
Yeah, I haven't myself done it. But like within ISTA, I can tell you that there's been a study in China where there's a heck of a lot more EV, not just private or individual BEVs or battery operated vehicles for people, but they also have more for truck transport over there. And so I've seen studies even done through ISTA that is starting to show data, and it does look much less intense, I would say, comparatively speaking. Now, is that a result of the electric propulsion, or is it a result of that the vehicles are new? They're basically brand new compared to a lot of the stuff that's on the road that seems like we get involved in measuring. It's probably both. I don't know enough myself, but I have seen it, and I would say it looks very interesting that it's lower intensity. And realize that some of the vibration that you do experience in truck transport is related to kind of the buzz of the engine or the transmission of that propulsion system. Although some of it's related to the vehicle suspension, and some of it's related to, let's say, tires and wheels as they rotate. So a lot of different things contribute to the shape of that PSD profile for any transport vehicle. And it's not just the propulsion system, but I would say that what I've seen looks like pretty good rides. Be interesting to do more, for sure.
Great, thank you. Next question is, why G2 hertz instead of just G?
I would say it's too hard for me to answer that here. It's addressed in that paper, pretty straightforward. So if it's okay, I would take a pass on trying to explain it in this conversation and say the answer is in that paper. And again, it's pretty straightforward. And if there's any questions after downloading that, your hands on that, I would be happy to try to explain further. And if someone's interested in that sooner than waiting for our dissemination of the recording, feel free to email me at the address there and ask for it, and I'd be happy to share that. Even that specific explanation, I can cut that right out of the paper and share that.
Thanks, Eric. Can you please explain the PSD obtained after importing? I mean, a technical explanation.
I'm not sure what that question means. You know, I can generate a PSD from field data. You know, I can go right now and just go hop in my car and collect, even if it was back out of the driveway. So if I record 2 seconds of data or 10 seconds of data, I can create a summary PSD from that, or I can just do it. I can export, you know, a 2-second PSD. So meaning a PSD from 2 seconds. If I can create that, and I can export that and import that into a vibration controller, and it's just ASCII data, right? It's 2-column ASCII data. It's that G squared per hertz in one column and frequency in the other. So I can export that from my data collection software, whoever, you know, was to collect their data. I can import that into a controller, and I can hit the play button, and it's going to be moving. The table will be moving with energy content that is representative of those 2 seconds. And if I say, well, I don't, you know, 2 seconds, that's not good enough. That simulates my whole ride down to, you know, let's say to the gas station back. If I do that, I might want to capture 100 2-second events as I drive to the gas station and come back. And then I average all that together, and I come up with one PSD that represents that to and from drive. I can import that, and I can run that, you know, hit the start button, and table will start moving, and it will move with, again, with the energy content that and dynamics that were occurring during my car ride. On average, that's what it felt like. That's what it looked like as I was going down the road. I don't know if that makes sense or not. I was talking up to the chair just for everybody. You know, I was talking, Sharon, that this is a topic that, you know, almost would be fun to do a full day or a half day in-person seminar, because it's almost, you know, it's warranted to address all the questions and see things with your own eyes as you're looking at data, and then how you move that data, for instance, potentially over into a controller to make sense of that. It's a good candidate for a seminar. And quite frankly, you know, these are courses that are taught in universities over a semester. Anyway, so that's something that we have in our back of our mind, is to maybe offer in-person seminars that touch on some of this more involved content.
Thanks, Eric. Another question. What is the recommendation to transport the goods according the PSD to avoid high vibration? Air, vessel, truck, maybe to prevent damage. The transport companies will take this information for it says norm, ISO, ASTM, to prevent high vibration, and that's a question.
Well, not 100% sure truly with the meaning of the question, but what I can tell you, you know, the modes of transport, I'll just say that my take, which I think is most people's take, is that between the different modes of transport, rail, intermodal, which can be truck or rail, but intermodal, truck transport, air transport, the worst ride you're going to ever experience out of all those modes is by truck. It's the most severe comparatively. It doesn't mean it's too severe, but it's more severe than any of the other modes. Air is the best. I mean, quite frankly, you know, ocean is the best. The best ride you're ever going to experience is where you can just kind of relax and not worry about it from strictly a vibration perspective. And why is that? Because when a big ocean, you know, a big cargo container is out on the sea, you think, oh, rough seas, maybe big waves. Yep, but that's not vibration. Especially, you know, on an ocean, the time period, you know, the cycle of waves, ocean waves, is huge and long. In addition to that, a cargo ship is huge and heavy, and so big, heavy things can't respond to vibration like comparatively smaller things. So whenever we do vibration measurements, and this has been the case my whole career, 30 plus years, we almost never record anything when it's out at sea. The ride to the port and from the port, yeah, you might need to be concerned with the handling at the ports, going on the ship or off the ship. But from a vibration, when we think of vibration testing in a laboratory environment that we all perform, if you think about it, there is no ocean vibration profile. And it's almost kind of similar from the air side of things. There used to be, the older ASTM air profile was actually pretty severe. And quite frankly, there's a lot of people that questioned, and myself included, where was the data that stood behind that profile, and it was hard to find it. And so there was an effort back in the mid 2000s or 2010s, late 2010s, to take a look at that and see if it needed to be changed. And it was changed, that air profile, because all the measurements that had been performed that what we were part of in that group showed low intensity vibration while things were flying in the sky, which there's a lot of, again, be a whole conversation of why that makes sense. But as someone who travels an awful lot by air, it makes complete sense to me that it's actually pretty darn gentle compared to over the road. So, and what's good to understand is that the standard profiles that are in ASTM or ISTA are considered accelerated. So when I talk about that method of going out and measuring things and all that variability that happens, what normally we do on people that summarize or characterize an environment is they take all that data from maybe 2 weeks or a week or 10 hours of journey, and we average it all together, and we come up with a PSD that is reflective of the average intensity of the ride. And so the way the standards organizations work is they say, well, if that data represents 20 hours of transport, nobody wants to, for the most part, most people don't want to run 20 hours of vibration in a laboratory. They didn't want to run 10. Less is always better from an efficiency standpoint. So how do you get to that point? How do I simulate a 20-hour journey in a lesser period of time? Well, the way you do that is you increase the intensity of the test, which allows you to shorten the duration of the test. And there is a accelerated testing methodology, almost like a formula that you use to direct how much amplification or intensification, acceleration of the test profiles that you perform, which is something you have to be very careful about. I would say, because you got to be careful that you don't over accelerate things by trying to short, like if you're trying to do 20 hours of transport in 1 hour of testing, you could run. You could use that formula or that methodology to come up with an answer, but the resulting test intensity would be so severe that it becomes unrealistic. It's like, wait a minute, you spit out a GRMS using that formula, it worked, but the intensity of that is greater than I would ever see or expect to see in the transport environment. So you got to be really careful about accelerating things, how you accelerate, so that you don't overdo it and your test becomes overly severe.
Thanks. We've got 2 more questions left. The next one is, probably the domain of waveform from the real world data is higher than the motion limitation of the equipment. How can we reduce the domain?
I'm not sure once again, exactly what that means. So let's say a vibration system, when we or anybody who manufactures vibration systems, one of the key components of a vibration system is the actuator, is the piston that the table is attached to. The piston moves the table up and down. And so that piston, one of the characteristics of speccing the appropriate size of a piston is how much stroke it has, how much it can move up and down. And forever, the industry standards as they exist kind of require, for the most part, about 2.5 inches of stroke to perform those industry standards. However, again, remember that there's averaging and things that take place in that whole standardization process. If you wanted to simulate the extremes, more of the 90th, 95th, 99th percentile, especially of the low frequency inputs, think of things like, I don't know, potholes or really rough roads where the suspension of a vehicle is really moving and hopping, especially if it was an air ride truck suspension, you'd need more stroke. You'd need more stroke. And, we make them, other people make them. We've made actuators with as much stroke as 9 inches. One of our standard is 6. Another standard is 4 inches. So the more stroke, the more you have the ability to simulate those big inputs. So, and quite frankly, the closer you want to get to simulating reality, I would tell you, the more you should be thinking about, having that additional stroke. That's not an insignificant thing, though, or change, because anybody, quite frankly, if you have our equipment or other people's, you can upgrade it. You can upgrade it, but it's not just a matter of getting more stroke in the actuator. Just because the actuator can move more to generate the oomph or the energy at that frequency, just moving up and down 6 inches, I can do that. But if I want to go really violent at 6 inches, then the next thing that you have to think about is the like in our case, the hydraulics, because they're driven by hydraulic power supplies. Fluid goes through the hoses to the actuator and makes it move. So just having bigger actuator or more stroke in your actuator is one thing, but then you need more power behind it or more fluid flow to get the response out of that actuator at the right intensities. So I think it's a real issue. Much data as I've captured, vehicles, containers going over bridge abutments where quite frankly, launches the cargo in the back off of the bed of the truck and throws it around. You want that capability, and that happens. It happens a lot. Then you need to rethink the type of testing hardware that you want to be able to simulate that. And those are extremes. Those are extremes. Most of the time, obviously, when you're transporting goods, things aren't getting launched. I mean, if you watch that video, I could show you hours upon hours of very boring video of what it's like when a container is going down the road on a truck or going down the rail. It's not exciting. There is movement. So vibration tests generally are the shaking, rattling that's going on as things are going down the road or over the rails or even in the air. There's a little buzz that's going on. All the other big nasty things in that whole process development of how we create those profiles, for the most part, those get averaged out, right? They get averaged out almost by definition of how we create PSDs. I think longer term, there's probably opportunity to say, give me, for instance, a standards organization to say, well, what about a rough road test, or what about a pothole test, whatever you want to call it, but what about a test that accounts for those big inputs that do occur? You want to simulate those. You might not want to simulate them for an hour or even 10 minutes. It's probably, can I simulate 1 minute's worth of that versus 4 hours versus of going down the road? I think there's a place for that probably moving forward if people really care about getting close to addressing all the hazards that are in the supply chain. But right now, there isn't a requirement for it.
Thanks, Eric. And then the last question. If
Yep.
you ship by air, ocean, and truck, what PSD is recommended to use during testing for general simulation?
What PSD?
PSD, yes.
Yeah, I mean, we participate in all the standards organizations, ASTM, ISTA. I'm on the board of directors of ISTA. I strongly believe in the development of their test procedures and a lot of the research that they've done. I'd say that ISTA has done, but membership of ISTA or research that has been sponsored by ISTA to go look at these environments and create those either the test procedures or the PSD profiles specifically that are used for the random vibration testing. And they have different profiles in those for those different modes. So I wouldn't say there's one PSD that I would recommend for a mode of transport. I would say in many cases, if you're going to ship, if somewhere in your supply chain you're going to ship by truck, but you also might then ship on an ocean vehicle, or you might even ship intermodal where it goes by truck and rail. If you have to pick one, I would certainly, if it's going to go by truck, I would pick truck because that's the worst it's going to be. So there's a little, maybe oversimplifying, but the idea of if it can survive that, it's likely going to have to be able to survive the other modes of transport from a vibration perspective.
Wonderful. Thank you very much, Eric. I think that brings us to the end of the webinar. As Eric mentioned, the live product update is coming up. So there is a link in the chat box. If you haven't registered yet, you're welcome to use that. And we'll also make sure that there's a link in the on-demand for you that you can register with. And again, as Eric said, please feel free to reach out to him, eric.jonassen@pptgroup.com. And yes, we hope to see you for our next webinar. Thanks, Eric. Thanks, everybody.
Thank you, Sharon. Thanks for all your help, and thanks people for sticking with for the whole duration.
Thanks,
Talk
everybody.
in a couple weeks. Thank you.
Have a good day. Bye.
Bye-bye.